So this is not the buildings we work in. This is the old city of Strasbourg, part of the fortifications. Our buildings are slightly toward the end. On the top right, this is the cathedral. And we are in the so-called city center campus. We have 3 campuses, and this is the city center one. Well, I'd like to start with a picture acknowledging the contribution of Alfred Werner, who is considered to be the founder of coordination chemistry. And this man, of course, you probably know him because during your undergrad in chemistry, you've probably had to make some Werner-type complexes. Iron, cobalt, nickel complexes surrounded with ligands like water, chloride, ammonia, etc. Typically Werner-type compounds. He's not the discoverer of coordination compound, but he's a founder because he rationalized the interaction between the ligand and the metals. And this year, we celebrate the 100th anniversary of this Nobel Prize in Chemistry. So I think I had to start my lecture mentioning him. Furthermore, he was born in the same city as me, Mulhouse, south of Alsace. This is another link I have with Alfred Werner. But of course, he ended up much better than I did because he got the Nobel Prize at an early stage. But at that time, he already moved to Switzerland. So he scored for Switzerland, not for Alsace. Never mind, a great man. So I'd like to address 4 topics in different lengths, so don't worry. It looks like a long menu, but eventually it will not maybe be that long, at least I hope so. And I will start by addressing this question of a NO and PO chelate, which are a family of chelating ligands that have become very popular for a lot of reasons, and they're metal complexes. And initially, we wanted to prepare catalysts for a reaction of industrial relevance, and I will give you some details later, which is ethylene oligomerization. And we ended up making magnetic materials. This is a very good example of something I'm a very strong advocate for and believer, is serendipity. Serendipity doesn't mean you do anything anytime, but you make a discovery by accident. You wanted to go in that direction, and you stumble something different that was not anticipated, which is sometimes far more exciting than the initial goal you had. But as the pastor said, serendipity or luck only smiles to the prepared mind. So that's the bottom message. Then we will move on to other topics that we will discover on time. So the reason why these chelates are so important is that because we have very simple ways in coordination chemistry to bring about selectivity in the structure of a metal complex. If you have here, in a very sort of cartoon way, a metal center chelated by a ligand of which the 2 donor groups have the same function, identical. By symmetry, the 2 positions here in violet, the trans positions, are identical. Stereochemically, there is no way to differentiate them. So if you wish, in terms of symmetry, they are degenerate. However, if you now take a heterofunctional chelate, the 2 donor functions now are chemically different. Immediately you lift the degeneracy. The 2 trans sites become different. So that's a very simple way to bring about selectivity. So the next question is, if I react these compounds with any substrate molecule, will the substrate recognize the site, trans to D, or trans to blue, or trans to red, in other words? So that explains why heterofunctional ligands have become so popular. This is also often called hybrid ligands, because it's half D2, half Y2. You combine them and you have dy. So that, of course, immediately asks you the question, can we use any type of chelate? Are the 2 donor functions always remain coordinated to the metal throughout a transformation or not? And we'll come back to that later. At the moment, the 2 chelates, the chelate here remains chelate throughout the transformation. They don't migrate, they don't open an arm, they remain chelate, strong chelate, but chemically differentiated in terms of D and Y. Now, the reaction we were particularly interested is the formation of linear alpha olefins. These compounds have a huge range of applications. In 2006, there were more than 3 million tons produced a year. But depending on the value of n, in other words, the chain length of these oligomers, the properties are very diversified. If you have C4 to C8, in other words, from butene to octene, these alpha olefins will be used mostly as comonomers to form high-density polyethylene or linear low-density polyethylene. These are massive applications for industry, and more than 50% of the market share of alpha olefins is on the C4, C8 fractions, so the so-called shorter chains alpha olefins. If you have longer ones, C8 to C10, they will be used as plasticizers after transformation, lubricants, surfactants, etc. And most of these alpha olefins are produced from ethylene by oligomerization. Here is the name of some of the companies which have developed processes along these lines. Now, in view of this information here and the growing demand for C4, C8 fractions, the so-called short chain alpha olefins, remember we want to do oligomerization. We don't want to make polyethylene, which would very long chain, shorter chain, but in particular the shorter one, C4, C6. You need to have a catalyst which is selective for these. And the reason for the interest in these systems is due to the fact that this is a very fast-growing share of the market. So the French Institute of Petroleum asked us one day, can you do something in trying to help us favor the formation of linear short-chain alpha olefins, these ones in particular. I don't have the time to go into the details of the growing mechanism, how you go from C2 ethylene to C4, C6, C8, etc. But it's a kind of stepwise growth. Each time you grow the chain, you have a mechanism in organometallic chemistry called beta hydride elimination, which produces the product and regenerate the catalyst, and you can go on for the next cycle. So if you want to make polyethylene, you don't want any elimination to proceed. You want to go straight to the end, incorporate as many ethylene molecules as possible. If you eliminate the growing chain too early, you just make a dimer, C4. So you have to sort of balance in between. To make C6, C8 is very challenging. The energy differences here are just a few kcal per mole. And that will dictate whether the catalyst is suitable or not. So these were the kind of questions at the onset. If you look at the literature, you find a number of systems that have been investigated by various groups which contain chelating ligands. And here I've just emphasized nickel as a metal, because this is a very commonly used metal which has a fantastic diversity in its chemistry. Here on the top left, you see a nickel compound which is querplanar, D8 electronic configuration, nickel 2, with a PO chelate. This is a phosphine enolate type structure. And this is the basis of a catalyst developed by the Shell company, a very successful process in homogeneous catalysis, one of the largest success worldwide of homogeneous catalysis in industry. SHOP stands for Shell Higher Olefin Process. And it's based on this organometallic nickel compound. A lot of authors, and this is a very important system. Now here you have another example when we now have symmetrical ligands, the chelating diimines that Maurice Brookhart and Gibson have investigated, which is also developed by BP Chemicals. But the others here are NO chelates, so PO chelates, NO chelates, and symmetrical chelate, as I said before. P donor, oxygen donor, N donor, oxygen donor, which all based on this system shown here with various groups. So we were interested to look at the systems affording this sort of structures because there are indications from the literature that this NO chelation can be very favorable towards the reaction we want to catalyze. So we started with very simple ligands, which is here an oxazolene type alcohol. This 5-membered ring is an oxazolene. If you react it with a ligand to metal ratio 2:1, with nickel dichloride, methanol, room temperature 2 hours, you form a dinuclear compound. Now you see the nickel centers here are in an octahedral coordination environment. 2 chelates per nickel, that corresponds to the stoichiometry. 2 bridging chlorides, and this is a dication, so the 2 chlorides here act as counterion. Now, X-ray diffraction studies show that actually these chlorides are not miles away from the metal center. They're actually stabilized by hydrogen bonding between the OH group of the alcohol functions. So the two external chlorides, if you wish, not coordinated with the metal, are still not too far away from the metal centers. They are here and there. For comparison, we thought it'd be interesting to take another heterocycle, which is well known, pyridine, which is now a nitrogen donor, but a 6-membered ring instead of oxazolines. We carried out similar reaction, and you end up with similar product and similar structure here. Now, in terms of catalysis, we performed them under comparative conditions to be able to draw some conclusions. It's always difficult in catalysis, but at least you do your best. We tried to look at the activity of the system for oligomerization. 30 degrees, 10 bars ethylene, 35 minutes. That is standard conditions in our lab. To try to be able to be reproducible first and to be able to compare data. And the metal loading is always 1×10⁻² in millimoles per nickel in toluene. We need in this catalysis to use a co-catalyst, which is chlorethyl aluminum. The function of this co-catalyst is twofold. One is to alkylate the metal center to generate the first metal-carbon sigma bond into which the ethylene insertion will take place, and then you start growing the chain. But you first have to have a metal-carbon bond so that ethylene can insert into it. These are mechanisms well established in organometallic chemistry. But in contrast to many people who want to use a very large excess of co-catalyst, either chlorethyl aluminum or methyl aluminum oxide, the famous Mayols, we use sometimes 500 equivalent, 1,000 equivalent of co-catalyst. The advantage that you scavenge all the traces of impurity because the co-catalyst is hydrolyzed. So that's a way to dry your medium. But it's a very expensive dry, not a system, not very green, because at the end of the day, you hydrolyze your co-catalyst and you produce mountains of alumina. So what you do with alumina? B, these co-catalysts are quite expensive. So our challenge for us is to use as little co-catalyst as possible. So these plots here show you the performances of catalyst 1, oxazoline-based, versus pyridine, catalyst 2, in the presence of 2, 4, or 6 equivalents of co-catalyst. And here we have the turnover frequencies. In other words, the number of times the catalytic cycle is operated per time unit. And here we have numbers which are quite high, 180,000. That's pretty good. So you can draw comparison. You see that already with 6 equivalents, which is quite little, you get decent activities. Okay, so now we think about varying the structural unit because we know that the ligand is going to have an impact on the catalysis. So is there a way to improve the activity or improve the selectivity? For that, we focused on these very simple systems. Pyridine alcohol with just 1 carbon as a spacer between the heterocycle and the alcohol, the C1 spacer, or a C2 spacer. Or here you can put in this position 2 methyl groups in the gem position. That will have an impact on the basicity of the proton because the increased electron tonicity through the methyl groups here for the C1 spacer or for the C2 spacer. So basically, with this family of ligands, which look very simple, you can already investigate stepwise a number of parameters. You can vary the length of the spacer. You can vary the acidity of the proton because of the electronic effect. The steric hindrance. The 2 methyl groups on 1 carbon do have a steric hindrance, so they tend to open the angle, the so-called gem effect that was very well known in organic chemistry already decades ago. And of course, the solubility may also be influenced by the substituents. So what are the consequences of that? And let me take you through some of the examples. We stick to the 2-to-1 ratio we had before. Now we have the 2 methyl groups on the C1 spacer. Before we had a similar structure with the C1 spacer without the 2 methyl substituents. So basically the structure remains unchanged. So the 2 methyl groups seem to have no effect on the structure of the compound. If you look at the catalysis and the similar conditions as before, we see again that compound 1 this time, the oxazoline-based system, has very high turnover frequency. So it's a very active system. Surprisingly, perhaps, but it's something that in catalysis you cannot always explain. Why is one system better than the other? You try to, but you can't always explain. This time, the oxazolene seems to be better than the pyridine, the red box here, which is still active, but not as active as the oxazolene one. What about the C2 spacer, the longer chain here? We now react the same ligand with a nickel precursor. DME is dimethoxyethane, which is a very labile chelating ether, easily displaced by an entering ligand. So you have a very nice precursor which can be used in a controlled manner. If you react these two in dichloromethane, you form again a dinuclear structure that was again established by X-ray diffraction. Again, you see that the counter-ion here, the chloride, is again interacting with the alcohol function by hydrogen bonding. And we will see that it is not totally innocent. Hydrogen bonding, of course, we know that in our bodies, hydrogen bonding and water are essential. Small energy differences make a big difference. In catalysis sometimes as well, hydrogen bonding is very important. Now, if you look at these systems here and compare with the dimethyl substituted spacer with the GEM dimethyl group, now you see a totally different structural type appear. Now we have a mononuclear compound, still with a 2-to-1 ratio in terms of ligand to metal, bischelating here. But we have a nickel center which is octa-coordinated with the two chlorides bound to the nickel center. And this is established by a X-ray diffraction. So you see here, between these two systems, you can directly identify the steric consequences of the two methyl groups here, prevent formation of a dinuclear species because there would be a steric clash between the methyl groups of each side. They would clash sterically. That's why the dinuclear structure is not favored, rather the mononuclear system is. So we have here a case where there is indeed an impact on the structure. Now the question is, how does that translate in catalysis? If I now first move to the 1-to-1 ratio chemistry, we start again from the same precursor, and I take my C2 spacer ligand with no methyl over the 2-methyl. In both cases, we obtained cubes, cubane type structures, with nickel, 4 stoichiometry, 4 chloride completing the octahedron, the cube here. And our ligand here is chelating the nickel center, and again you see intramolecular hydrogen bonding interactions between the alcohol and the chloride ligands. The same applies to both structures. And this is rather rare. Cubanes are ubiquitous in a number of systems, including in bioinorganic chemistry, iron cubanes, etc., etc. It's a structural type which is well known. With nickel halides, surprisingly, very few, none to our knowledge, with triply bridging chlorides as corners in the cubane substructure. And that was established by X-ray diffraction here. So that we see in both cases a similar structure. So in this situation, the GEM dimethyl group do not seem to influence the structure of the product, in contrast to what we've seen before. So very subtle differences you have to investigate first. Now, if you look at the systems here, you can investigate them for catalysis, but of course, since nickel can be dimagnetic in its electronic configuration or paramagnetic and paired electrons, you wonder whether a polynuclear system would not be interesting to study in terms of magnetism, molecular magnetism. So we collaborated with some physicists in another campus in Strasbourg who are specialized in molecular magnetism and say, yeah, this system is interesting because it has a behavior of single molecule magnet. So, you know, this is something which people are quite interested in, to have information storage on basically a molecular dot that would have hysteresis properties, molecular magnetism, SMM, single molecule magnet. So you don't have the bulk, which has a magnetic property, but the individual molecule has. So we started this project to prepare pre-catalysts for ethylene chemistry. And now we end up having compounds that have properties in molecular magnetism. So that's something which was not anticipated at the beginning of the work. So now let's continue and see what happens still with the 1-to-1 ratio. We have this alcohol function, as I mentioned before, and we thought maybe we could modify not only the electronic properties of the ligand and maybe of the catalyst, but also the solubilities, by trying to deprotonate these OH groups here. So we reacted this cubane with the chloride apices here with sodium hydroxide. Instead of deprotonating the alcohol function, we substituted the chloride with hydroxide groups coming from the base. And that shows you the importance of the hydrogen bonding. This hydrogen here is not very acidic, and it is very much stabilized by this hydrogen bonding interaction. So the sodium hydroxide, a well-established base, does not behave as a base here. It behaves as a nucleophile. It substituted the bridging chloride with hydroxide. So now we have another candidate for catalysis and for molecular magnetism, which again revealed single molecule magnet behavior. Now, in the presence of base, as I said before, you may be able to fine-tune the properties because you change the electronic density at the metal center. You have a metal which is going to be more electron-rich. And also we had realized at an early stage that this compound is not very soluble. When we ran our catalysis in toluene or chlorobenzene, not very soluble. So I thought maybe if we could transform this ionic structure with the two external chlorides, you know, they are hydrogen bonded, but still they are not ligands, they are counterions. If we could just deprotonate two of the alcohol functions and remove two equivalents HCl, we would form a neutral species. And this neutral species might be more soluble in toluene. And that may be a bonus for the catalysis, because we are performing the catalysis in this sort of solvents. So I asked my students to take a strong base, sodium hydride. That's a rather strong base, stronger than sodium hydroxide, to react it with this compound, which is sort of red. Turn dark green. If you want to run NMR spectroscopy, bad news, everything is broad, you see nothing, because the compound is paramagnetic. So then the only thing you have to do is grow single crystals and run to the diffractometer. It took about a year to achieve producing X-ray quality single crystals. Fortunately, my PhD student was doing other things at the same time. You have to leave your Schlenk tube in the fridge. You check every week or 2 weeks whether some crystals grow. If not, you have to re-prepare a solution. Rather tedious. But we knew that this stuff here was catalytically active. And we had no idea of the structure. So it took a while. And when we got the crystal structure, we brought them to the crystallographer, and it took him about a month, literally, to solve the crystal structure. But that was not his fault. It's because we couldn't provide him with much information. Nowadays, in one afternoon, you get an X-ray structure solve of single crystals. It took months, because the structure was far more complicated than anything we had anticipated. And let me explain you what it is. This is a complete view of the metal core plus the ligands chelating the nickel center. The blues, the nitrogen of the pyridine, the reds, the oxygens from the alcohol function. And here is the core without the ligands around. So what do you see? An oxygen, 3 nickels, 3 oxygens, 3 sodium, 3 oxygen, 1 nickel. So the 3 nickels on the top here, they are part of a sort of incomplete cubane type structure. You've seen the cubanes before. We have here an incomplete cubane. The bottom nickel here is octahedrally coordinated by 3 chelating NO ligands. So that's the one here. C is a bottom nickel, 3 kind of propeller type chelating ligand. The top part is represented here with the 3 nickels here and the oxygens forming an incomplete cubane. So that structural motif was totally unpredictable. But even more so, what totally unpredictable was the incorporation in the product of the cations. That were the counterions of the base. We had no idea that the sodium would get incorporated into the product. And that, of course, a very important information. Because if we wanted to prepare this catalyst in situ, say, you know, the hell with growing single crystal, we'll never do it, make it the one pot in situ into the reactor, add the base, run the catalysis, and let's see what happens. It happens, something works. But what is responsible for it? You have no idea. This sort of black box chemistry I don't particularly fancy. Now, at least by having isolated this, we know that is one of the possible structures. You always have to be careful. One of the possible structures that could be generated in situ. But very importantly, it tells you that the choice of the base you made here can be decisive. It can have a structural effect because the cation ends up in the product, whereas initially you just wanted to have a hydride source to deprotonate the alcohol. Now, if you look at another view of the structure, you see here basically these two incomplete cubanes sharing a missing vertex. There is nothing here in the middle, but that's another way to look at these cubanes that perhaps is more familiar to you. At any rate, once you know the composition of the product, you can adjust the experimental conditions, optimize them, and make sure everything becomes reproducible and self-consistent. Now, if you now take the same precursor as before, and we go for the C1 spacer, 2.8 equivalents or 2.4 equivalents, with the same base as before. Here we find another kind of structural arrangement, which is a planar structure. All the nickel atoms are in the plane of the screen, forming kind of a wheel with a nickel in the center. And again, here you can easily recognize incomplete cubanes sharing elements between them. If you have here slightly more ligand to metal ratio, the central position is occupied by the sodium cation. Instead of divalent nickel 2, you have monovalent sodium 1. So you can selectively incorporate now the sodium in the center of the wheel. That, of course, again, for catalysis is very important to know. If you look at the structural motif, and if you take here this three-dimensional polyhedral view that are often used in solid-state chemistry or in coordination chemistry, you see here the octahedra sharing edges here. And this is a structure which is very common in a completely different area of chemistry, which is that of polyoxometalates, high oxidation state molecular oxides, the so-called POMs, polyoxometalates. They have the structure which is named after Anderson type structure. So that's always fascinating for me to see that from different areas of chemistry, you suddenly converge to structural motifs that have been seen in other areas of chemistry. There are some links there. So this one here has very weak intramolecular interactions. That's, of course, ideal to study the magnetism, because here you know that the center of the wheel is diamagnetic. Sodium plus has no magnetic properties, closed shell structure, that you can compare with the isostructural system with the nickel 2 center, which is paramagnetic here. So you can compare the interactions between the center and the periphery and between the nickel centers at the periphery. And this one has both ferromagnetic and antiferromagnetic interactions. So really, you can see that this nature of the central ion here has a strong impact on catalysis. I don't want to go into the details, but also on the physical property that is here molecular magnetism. And you can go on and now try to see whether you can convert one structure into another. So for example, we took the wheel structure here that will react with more nickel in order to decrease the nickel-metal ratio to go to 1. And indeed, you can form the cubane. So basically, you can see that these clusters, coordination clusters, historically clusters could only be called clusters if you had direct metal-metal interactions. But in the Fe4, S4 clusters that are very well known in bioinorganic chemistry, the distance between the ion clusters may depend very much on the oxidation state. So sometimes there is interaction, so sometimes you can call them clusters. It's borderline appellation, but you can. But you can convert one structure into another, which is very important because that depends on the experimental conditions. So if you're not careful, you think you have one structure in your bottle, but eventually under reaction conditions, you may convert it into another one, which might be more active or less active, display different magnetic properties. So the fine-tuning of the metal, ligand, and base ratios is very important. And you have here a huge diversity of options. Again, if you were doing in situ catalysis, you would miss all that. You would have no idea of what you have in your reaction mixture. So no way you can assign a property to a given molecule. And that, I think, would be very frustrating. And you can go on. I will not go into all the detail, but you can optimize eventually is a synthesis to get to certain types, that the one I have shown you before, with the sodium incorporated. By varying the ligand, the ratio, you can go to far more complicated structures, which I will not detail, which again contain sodium cation, nickel cations, hydroxide ligands. And here you can see this is the same compound, a nickel 6 sodium 10 cluster, which again can be analyzed in terms of cubane subunits linked to each other. And I think this is also, conceptually speaking, an interesting point that shows that these entities can be actually attached to each other to form superstructures, but all belonging to coordination chemistry, because we have metal-ligand interactions here, which are clearly coordinative bonds. In catalysis, as I mentioned earlier on, you often need a co-catalyst. I mentioned chloroethyl aluminum as a typical co-catalyst, but also we have in chromium catalysis, which is very well known for the Phillips process, which is running industrially, we have a number of co-catalysts which have different properties, but you need them. And very often, again, this is a kind of a black box. You add the catalyst, you add the co-catalyst, you close the reactor, you increase the pressure, and see what happens. But really, we don't necessarily always understand, well, what is the function of the co-catalyst. Roughly speaking, as I said before, you need to create a metal-carbon bond in order for the ethylene molecule to insert into it. But you also need to make the metal center more electrophilic, forming cations. And that's often the property of the co-catalyst. By making the metal center more cationic, you make it more, you increase the affinity of the ethylene substrate for the metal center. So roughly speaking, there are two key functions that the co-catalyst should have. But in detail, we don't always understand what happens. So I'm taking here just one example of a chromium-3 complex, which has here a tridentate ligand, 2-pyridine attached to a phosphine group in a facial arrangement in the octahedron, and 3 chlorides. And we reacted this compound in the presence of various co-catalysts for ethylene oligomerization. It is a rather active catalyst. But then I said, it'd be interesting to see whether we can isolate anything from the reaction of the pre-catalyst with the co-catalyst. We took triethyl aluminum, and what you see you can isolate is the alkylated compound. Ethyl group coming from the aluminum has replaced 1 chloride, but only 1 chloride has been substituted. I'm not saying that this transformation is quantitative, but this is the compound we could isolate and characterize fully. So we always have to be cautious. I'm not saying that there is complete conversion, but at least that compound was formed. If you take now methyl aluminum oxane, which is the famous Mayo, you replace partly this chloride with a methyl from methyl aluminum Mayo, but there is a disorder, crystallographic disorder, so there is still some chloride here. So in both cases, these catalysts have operated as alkylation catalysts. They've alkylated the metal center. Now you take these other 2 catalysts, very popular, trimethyl aluminum, the little brother of the triethyl aluminum, just a shorter chain. It does something totally different. It does alkylate the metal, but also it abstracts some chloride ions. So now we only have 2 chlorides left for the 2 chromium atoms. So the aluminum has picked up some of the chloride and made this a dication. So that's another important function, as I said, of the co-catalyst. It makes the metal center more electrophilic, so more susceptible to react with ethylene. And if you take chloroethyl aluminum, we see no alkylation product, only chloride abstraction to form now this dinuclear species with 3 doubly bridging chlorides. Let me emphasize again, I do not claim that these are the only products of the reactions. These are the products we could characterize. At least it triggers your imagination to think of possible scenarios when you have your precursor reacting with various co-catalysts. Why do some co-catalysts have different function than other co-catalysts? Maybe related to the diversity of products we could isolate in these reactions. So that's a way to trigger your curiosity. But I'm not claiming that these reactions are quantitative. It is very difficult to separate things from that reaction mixtures. Another way often to activate a metal center to make it positively charged is to remove the chloride. And typically, we use in inorganic chemistry chloride abstractors, which are very well known that you may have used in your first year undergrad or maybe even in school to run experiments with silver nitrate to precipitate silver chloride, or thallium PF6, which precipitates thallium chloride, poorly soluble. This is a driving force for the reaction. So I say, let's try with our complex, a bispyridine phosphine trichloride that will react with the co-catalyst before. Let it react it with a non-alkylating reagent, but just an electrophilic reagent, thallium PF6, expecting that thallium chloride would precipitate out. So I asked my student, run the reaction, tell me what happens. Came back to me, said, well, there is no thallium chloride precipitation. I said, look, this is in contrast to what you've done in first year university. Thallium chloride should precipitate out. Say, no, it doesn't precipitate. I can't repeat the experiment. I want to see it. Like St. Thomas. Sometimes I like to see things. Otherwise, I don't believe them. Well, indeed, there was no precipitation of thallium chloride in dichloromethane. But he was able to isolate compounds from that and single crystals. And the answer came, the thallium has not abstracted any chloride. It has coordinated to this free chloride to give this sort of product in the structure is shown here, with the PF6 stabilizing with fluorine bonding the thallium center. It forms sort of a dimeric structure in the solid state, which is quite nice, but I don't want to go into the detail. The message is here, if you use typical chloride abstractors, and this is not the first example in our hands, they don't always behave as chloride abstractors. And that very much depends on the solvent. In dichloromethane, often you add the electrophile to the substance instead of removing the chloride. If you go to acetone, a totally different game. So again, this should trigger your curiosity. We should always be careful and cautious about what we say, because there are always exceptions. But these can be very important, of course, in terms of reactivity and catalysis. Let me give you a brief example of another behavior for the chelating ligand, applied this time for titanium, which is another key metal in ethylene chemistry for catalysis for ethylene oligomerization or polymerization. You've all heard of Ziegler-Natta catalysis. That was based on titanium. Again, we have the chelating system that I have shown before. Before, my chelate was always a stable chelate remaining attached to the metal center throughout. But there are cases where the chelate can undergo what we call a hemilabile behavior. In other words, in solution, the chelate can open up one of the dative bonds to the metal, creating a vacant coordination site. In this position, if you remove the donor blue, or on that position, if you displace the donor red. Why is this notion important? Because this will occur in solution. And you can observe this opening and closing mechanism by variable temperature and mass spectroscopy. There are compatible time-scaled experiments. Well, in solution, if you have this vacant site, a substrate can come in, coordinate to the metal center, be transformed at the metal center, if this is a catalytic site, transform the substrate into the product, and now chelation will provide a driving force for expelling the product and reforming the catalyst. So you have this hemilabile behavior operating for you in two ways, opening the gate when needed, but closing the door to expel the product. And that's why this concept has become extraordinarily important in the reactivity studies and in catalysis, because this is something you can monitor by NMR spectroscopy, and that can be very helpful in terms of promotion of molecular transformations. And this has been applied to a number of reactions. No way, sorry, the slide is very busy, just to show you the diversity of organic transformations that have been now catalyzed with the help of hemilabile ligands. So no wonder that this is becoming a very popular concept and a very helpful one. A number of reactions here, and you can find the details in the literature if you're interested in, or if you need more detail, don't hesitate to send me an email. I'll be happy to provide you with more data if you wish to. Now let's apply this to titanium chemistry. Titanium, as I said, is a good catalyst in ethylene chemistry in many examples. We were interested to look at the chemistry of aryloxy titanium 4 compounds. And typically you will form them by reacting titanium isopropoxide with an OH group from an aryl derivative, and you will displace some of the isopropyl group in the form of isopropanol and incorporate your aryloxy moiety. So we started by looking at the monoaryloxy tris isopropoxide system. And we now compare two systems. This aryl group had the methyl group here, tertiobutyl here, and a rather bulky substituent in opposition to the oxygen. And the compound you isolate is a titanium-4 compound, tetrahedral coordination geometry, what you would expect. Titanium-4 is usually tetrahedrally coordinated, and the 3 isopropoxide. But if you have in opposition here to this group a small h compared to this bulky ligand, you don't get a mononuclear species. You get a dinuclear titanium, still oxidation state 4. It's not a redox reaction. Titanium remains titanium-4. But now we have a dinuclear structure with isopropoxide bridges. These OR bridge ligands can bridge, be terminally bound, or can be bridging ligand. A great diversity, very versatile systems. So that's why the structural chemistry of this system can be rather complicated, because they can undergo different type of bonding modes. But here you see, again, if you had not isolated this species, it would be very difficult to know otherwise that you have a dinuclear species. If you want to engage that in catalysis, I think you better know what your precursor is, at least what your precatalyst is. Now, when we replace this group here, which is non-coordinating, it has no dative function, with an amino group here, which could potentially perhaps coordinate to titanium, although titanium doesn't like nitrogen ligands very much, but it can. We looked at the NMR, and if you look at the NMR in the CH2 region here, or to the nitrogen ligand, at room temperature, you see sort of a singlet, which splits into 2 doublets at low temperature. So 2 doublets, a typical signature of an AB system. So 2 protons become diisotopic, you have an AB spin system, 2 doublets. But at room temperature, a singlet, which means you have here a dynamic behavior. We suspected that this dynamic behavior would involve coordination of the nitrogen to the titanium center. If the nitrogen remains non-coordinated free, no way you can generate an AB system. So 2 CH2 remain equivalent. You get a singlet. But if they coordinate to the metal center, then they should give rise to an AB system. But this crystal structure did not reveal any interaction. However, if we now move to the methoxy analog here, we could characterize the compound by X-ray diffraction, and now we see a mononuclear titanium center, which is octahedral coordinated, and the 2 methoxy groups are actually coordinated to the metal center. So in a way, it makes sense, because titanium-4 is much more oxophilic than nitrophilic, if I may say so. It prefers oxygen donors. But still, I believe that in solution at low temperature, the form preferred, privileged, is the one where chelation of the nitrogen to the titanium center occurs. So then we have this hemilabile behavior, this opening, closing of the gate, which, as I said, is key for catalysis. That may have some implications for there. This is the compound I have just showed you before. But now if we compare the chemistry with this precursor and with the silyloxy derivative, instead of having the negative charge, I have a trimethylsilyl group, which is a good leaving group. You would expect basically the same thing, but it doesn't happen the same way. What happens here is that we don't form a mononuclear system, tetrahedral as before, but we form again a dinuclear system, where now the methoxy unit is bridging between the titanium center as established by X-ray diffraction. So the message is really here that you see the subtle changes brought about by a variation in the ligand design, either sterics or electronic. Some of the syntheses may be under kinetic control, and that's why these differences are very important. Not all the products are under thermodynamic control, and that's something you have to check before. So how does they compare in terms of catalysis? We compare the tetraisopropoxide, the precursor. We take the aluminum triethyl as a co-catalyst. We keep the same ratio throughout. We compare it with the bisphenoxide and with the one that has the hemilabile behavior. And if you look at the productivity in terms of gram per gram titanium per hour, we were quite happy to see that the most active was precisely the one which we suspect has heavy labile behavior. And in terms of selectivity, all of them are very selective for C4 alpha olefin, for 1-butene, terminal alpha olefin, much more than for C6. So basically, you have a very selective catalyst for ethylene dimerization into 1-butene. Let me come now to the final part, which is dealing now with cluster compound. I mentioned this word earlier on, which implies the existence of metal-metal bonds. So this is an area which we've investigated for many years. Beyond the synthesis of such clusters, because this was, still is to some extent a challenge, how can we make on purpose specific metal clusters, knowing the nuclearity, the size of the core, the nature of the core, are all the metals the same or different, etc., homometallic, heterometallic. We had an idea a long time ago, that was in the early 80s, to consider these metal clusters. General formulation was Ma. Most of them came from metal carbonyl chemistry, to deposit them on inorganic supports, alumina, silica, something you may use for chromatography, for example. If you impregnate a solution of that, thermally activate, you should be left with a metal nucleus which corresponds to the core of your molecule. You've stripped off the ligands, you are left with a metal core. What is the size of the metal core? Is it the same as that of the nuclearity of the precursor? I've taken here A and X because we don't know whether the particle will remain very small or coalesce into larger particles. More importantly, we have a bunch of mixed metal precursors available, where the two metals here are different, chemically speaking. So if you activate them after deposition on support, the question is, are we going to generate very small alloy particles, or are we going to observe phase segregation, formation of particles M1 next to particles M2? If we can keep the alloy throughout, this would be a very nice, soft, very mild conditions I use here, a very soft way to generate metal particles that may not be able, that one cannot generate necessarily from conventional methods. So that could open a number of perspectives. So the idea was, of course, can that be made? Can we obtain bimetallic particles? Can these molecular alloys, I quote that here because this is not a proper alloy, but you understand the message. The two metals are in close proximity in these nanotype particles because they have nano size. You can even think of making metal particles, of metals that are not miscible in the bulk. If you take, for example, ruthenium and gold, we can make mixed metal clusters with ruthenium and gold, but you cannot form an alloy. These two metals do not mix. So if you can have this approach available, maybe you can reach metastable phases that would not be accessible otherwise, and they could perhaps have unique properties. So perspectives, of course, very interesting in terms of using microporous or mesoporous supports to condense the clusters, to anchor them. I will show you examples, and of course, to see whether we can control this thermal decomposition. The first candidate, and that's back in the early 80s, and this is, I think, the very first example of a molecular cluster used as a precursor to nanoparticles. At that time, to put things in perspective, we were very pleased and proud in my group to make compounds that we thought were aesthetically very pleasing. Here is a palladium-2 molybdenum-2 cluster, a planar structure, a center of symmetry, phosphine ligands here, cyclopentadienyl and carbonyl ligands around the metal centers. So that structure was very unique. This was the first palladium mixed metal cluster ever reported, so we're very pleased with that. So when I came up with the idea to use this guy, to put it on silica or alumina, thermally activated to decompose it, and look at the metal particles resulting from the decomposition, a lot of colleagues say, Pierre, you're absolutely nuts. You spend your time trying to make nice molecules, now you want to destroy them thermally. Are you totally crazy? So, if you get something more exciting at the end of the day, what's wrong with that? Nowadays, lots of groups worldwide are using this approach to generate nanoparticles. So sometimes, you may have a crazy idea, but which turned out to be a fruitful idea. So we took this cluster, the core composition is palladium-2 molybdenum-2, and tested it for this reaction, which is a carbonylation of organic nitro, aromatic nitros, to give isocyanates plus carbon dioxide. That was done in collaboration with a French company called Atochem at the time, which was a producer of isocyanates. Isocyanates, of course, are very important organic chemicals, precursors to polyurethanes, etc., tons here. The classical way to make isocyanates is to use amines plus phosgene. Well, even if you're not an experimental chemist, you've heard of phosgene. It's usually bad news. It's not sort of very green in terms of the surrounding. Industry can handle phosgene. But if we could have a milder way to get to isocyanate, that would be nice. And nitros would be a good candidate because they are usually the precursors to the amines. So if you take the phosgene route, you first have to reduce nitros to amines anyway, which is costly, and then use phosgene. Carbon monoxide is cheap and readily available. So that could be the reducing agent and form directly the isocyanate. So I said to the company, try our catalyst versus your own catalyst. I don't want to know what you put in your system. Just make sure two things. Everything should be run under comparable conditions. If you add salt and pepper at some stage, add salt and pepper to our catalyst as well. But keep the same metal ratio as we have here, 1-to-1 ratio, to be really comparable. And our system turned out to be better. Now, the beauty of this reaction here is not only the simplicity, but it is telling a lot about the nature of the catalyst. Because molybdenum provides activity, palladium provides selectivity. If both are high, you get isocyanides in very high yields and very high purity. Otherwise, if you have leaching of one of the two metals, you immediately see the conversion drop, the activity drop, or the selectivity. So you can have a chemical tool readily available here. And then we did the same approach with iron palladium catalyst, which from the patent literature was also employed for conventional heterogeneous catalyst. You mix the salt, you stir palladium chloride, molybdenum oxide, you stir, cook, etc. But here we have a molecular-based approach to the system. So in other words, that can be actually applied to the formation of new heterogeneous catalysts. These are the iron palladium precursors that we use. You can see we can modify the palladium to iron ratio, 1-to-1, 1-to-2. And here we extended that to an organic derivative, which is the autonitrophenol, which from this heterocycle, which is benzoxazolone. And again, we found a much better activity and selectivity using the cluster-derived heterogeneous catalyst. So the particles here were all found to be in the 2950 angstrom in terms of the range, at least those we could see. At that time, of course, the sensitivity of the techniques was not as high as now. So if the particles were too small, they would just not be seen, which doesn't mean they were not present and maybe not active. That remains always a question mark you have to keep in the back of your head. So we thought about another way, or maybe a more refined way, to anchor clusters into porous materials. Typically, you have the precursor, which are the carbonyl clusters I mentioned, homo-heterometallic. We want to have oxidation state as low as possible in the precursor, so that when you strip off the ligands, you don't really have to do a drastic change of the redox properties of the core, to minimize the transformation. Basically, the molecular striptease we're doing to the terminally should be very soft. Just remove the ligands without massive redox chemistry. You can use to impregnate your cluster different matrices. You can use mesoporous silica xerogels prepared by the salt gel methods, just incorporate, or organized mesoporous silicas like MCM41, SBA15, which have a porous structure. And the idea is, can we put the clusters into the pores and have, in addition, a confinement effect due to the size of the pores? And after thermal treatment, obtain metal particles that will be analyzed by various methods. So we want to have low oxidation state clusters. So one of the candidates we took was this tetrahedral iron or ruthenium cobalt-3 cluster, only carbonyl ligands, which can be easily removed thermally. And this metal were chosen because the physicists we were collaborating with were interested in magnetic properties of cobalt nanoparticles in the presence or not of a second metal, like, for example, iron or ruthenium. So these were the candidates we selected. Impregnation is a way we classically do, like when you prepare column chromatography. But if you want to have a stronger interaction of the cluster with the support, you can think of a grafting mechanism. And then by covalent attachment of the cluster to the support, you may have a better control of the loading of the cluster and the dispersion of the cluster into the support. So we use different approaches, and here is typically an example of a linker we use to attach the cobalt-4 cluster to the support with the OH groups by having this diphosphine functionalized here to nitrogen to an alkoxysilyl group. So this bifunctional linker is a kind of a hybrid ligand. Two sides contain the phosphorus, the other one contains the silicon that will be attached to the surface. And that will allow you to make a covalent attachment, if you wish, to the cluster. You have basically two approaches available to reach that goal. One is to start from the matrix, and you react the matrix with a cluster already decorated with a functional group, and then you condense the functional group with the OH on the surfaces. That approach, called A here, requires that you can make such clusters, which have already been pre-functionalized. And that's exactly what is shown here. Just to give an example, you can have here a cobalt-4 cluster with a ruthenium here, and an alkyne, a CC triple bond initially, linked to this attachment here to the silyl group, which contain the OR functions. Or here a tetrahedron with cobalt-4, and again, at the end of this diphosphine, you have this alkoxysilyl functionality. So a pre-functionalized cluster can be made. So that approach can be a valid one. Alternatively, you can have the second approach where you first functionalize the matrix with the diphosphine groups, for example, waiting here for the cluster to come in, and then it will accumulate to the cluster and form the desired hybrid material. So we took here these porous alumina membranes, which have a honeycomb structure that you've probably seen before, with pore diameters between 7 and 250 nanometers. This is an AFM view of the top. You see basically a bunch of cannellonis. And the idea is to put something specifically into the cannellonis in an anchoring procedure. So we took this approach here. We take the membrane, this aluminum membrane, that we react with our ligand to form the diphosphines here, which are pendant. We first tested the concept by using gold colloids, which can be prepared in a very reproducible manner since Faraday, 30 nanometers, and we could actually see that the gold colloids are immobilized into the channels of our cannellonis. So you can wash the cannelloni, what has been hooked up by the chelate remains there. Then you can open by a macrotome system, you can cut the pores here and look by TEM at what is inside. The particles here have exactly the same size as the precursor. So this is a very soft approach. You have not coalesced the particles into big ones. So this system is a viable approach. So we applied that now to the cobalt system. We've tried first to react the functionalized cobalt-4 cluster with the tail here with the OH group on the surface, but that did not work. Probably our explanation was that this is already a very bulky molecule, and it doesn't enter easily into the channels for steric reasons. So then we did the other approach. We first functionalized the matrix. We have the diphosphine groups here waiting for the cluster to come in. This one is smaller in size compared with that one. It doesn't have this extra functionality. Enters into the pores, and when it enters, it substitutes here in this position. That's something we know exactly for sure. So now we have our anchored cluster, and we can perform thermal decomposition. You look at TEM, and indeed you see in the channels of your matrix small metal particles. That was done with SBA 15. So the particles are uniformly distributed. This is the histogram, and you see that the size is about 6 nanometers, and that corresponds to the diameters of the pores, which suggests that indeed we have a confinement effect. the particles do not grow too big because they are confined by the diameter of the mesoporous materials. The surprise was that we did not form cobalt nanoparticles, but instead cobalt phosphide, a CO2p phase. Of course, the phosphorus comes from the phosphine ligands. But that was intrinsically a surprise, but interesting. Now, the fact that the particles are really inside the porous material is shown here by tomography. This is the cut of the support. The red dot are gold standards to have an evaluation of the size. But the little blue spots you see are the nanoparticles. They are really indeed inside the cavity of the mesoporous materials and not outside. So these CO2p phases can be interesting in their own right. They have the paramagnetic properties. The size is very much limited and defined by the matrix, much smaller than if you take zero gels, and potential application in catalysis and also maybe for electronic properties. But again, that's something interesting. Very briefly, I'm running out of time, I apologize for that. This tetrahedral cluster, now we decorated with the thiol function, of course, to deposit them on the gold surface. Thiol functions like gold very much. So we had here this possibility to arrange these molecular clusters on gold 111 faces and try to look at the self-assembly. And then you can do a similar trick with the ruthenium cobalt clusters where you have the SH functionality here on the surface. So you can actually apply the concept to various systems. And I'm just skipping this one because, no, I cannot skip that one quickly. In the process of looking at these thiol functions, we realized that the thiols here are very easy to oxidize to give you a sulfur-sulfur linkage, a disulfide. So you can link actually two such clusters with the SS link. But the beauty is, if you take this cluster, which is much more stable towards air than the thiol on the gold surface, the gold surface will break the SS bond and form directly a S-gold interaction. So basically you attach two clusters in one shot. So that gave us the idea to try to explore this possibility, starting from this organic ligand, which is well known, a tetrathioether, which we decorated with 1, 2, 3, 4 diphosphine moiety, which we now want to use to attach cobalt clusters on these, and now you can form this sort of dendrimer-like cobalt-16 cluster. How do we know that? By X-ray diffraction. Very tedious to grow the crystals. This system is very difficult to handle, but at least we could be sure that indeed we have this sort of a short bite ligand on the diphosphine functionalized here, assembling this nanocluster whose size is shown here, 30 angstrom by 11. Basically, once you have that on the surface, we should be able to observe them by various spectroscopic methods. And finally, in the cluster surface analogies, there was an old concept around that these metal clusters could give a model of how small molecules interact with surfaces, in particular carbon monoxide, because of the beautiful work done in Cambridge in the group of Jack Lewis, which produces osmium-20 carbonyl clusters, and the way the carbonyl ligand is attached to the super tetrahedron of the metal core is very much like CO on a 111 metal surface. So that gave the idea that the molecular species here could provide structural models of interaction of small molecules on metal surfaces. And this has also been extended to organic molecules like benzene. Again, this work came from Cambridge. The first benzene molecule attached symmetrically to a metal cluster in a triangular manner. So benzene has been investigated. And you see here the various sites on which the benzene can interact with the surface. All these examples have been identified with molecular clusters. So these is a very good match here. One ligand which has been much less investigated is cyclopentadienyl, C5H5 minus. In contrast to benzene, which is neutral, C5H5 minus, a very good ligand in organometallic chemistry, has barely been studied on surfaces. Now people have looked at, particularly in physics recently, at copper 111 interacting on various sites here with a C5H5 ligand. And they found a lot of interesting observations, but there was no molecular model of a CP interacting with 3 metal atoms, in contrast to benzene. We have examples of cyclopentadienyl interacting with 2 palladium centers, including here's the bridging ligand, but there was no example of CP interacting with 3 metal centers until, fortunately, a good postdoc in my group was able to produce, I should confess it was not designed, a palladium cluster in which, now I don't go into the detail, one face of the palladium butterfly is capped with a triply bridging cyclopentadienyl ligand. So now we have here a mixed valence cluster which displays this interesting structural feature, the first CP minus ligand interact with surfaces. So that expands the scope of the metal, of the cluster surface analogy which I mentioned earlier on, and there is a lot of scope in that people can reinvestigate in more detail. Conclusions are that we can use all the new ligands, you can coordinate them to metal centers, you often get unexpected structures that can lead to interesting physical properties, chemical properties, in the case of some special metal centers and biological activities. The novel bonding modes can trigger new concepts, new reactivity patterns, which have often relevance to catalysis. And if you take the clusters as examples here, you see they can lead to new nanomaterials, particles, rod, thin films, etc., with various applications more towards heterogeneous catalysis or physics in some cases. Often you encounter surprises which may be disturbing because it implies you have to develop a new way of thinking, but that's exactly what is stimulating and challenging. So I'd like to thank a number of people, particularly those in blue, who were involved in the chemistry I presented today. Some permanent people, Jackie Rose, Andreas Anopoulos, the visiting scientist with us, fantastic chemists, some postdocs from various countries, PhD students, also very international, a lot of collaborations because this is an area where we need that. I hope these agencies pay the bills. So just finish by showing you where Strasbourg is. Some people wondered which side of the Rhine River it is. It is on the left side, so it's part of France, very close to the border with Germany, but very central in Europe. It is typically located here in the east part of France. The cathedral is well known. Outside, you see very hilly landscapes where wine is produced, particularly white, but also some red Pinot. The old house with the timbered houses here, typically from the Middle Ages. It's an old city which was founded by the Romans 2,000 years ago. We're grateful to the Romans for importing the grapes into Alsace, so that's why we now have wines. The rose window in the cathedral is very well known, of course, and pictures of the city centers. Please come anytime and visit. Thank you very much for your kind attention and patience. Right. We decompose thermally the cluster after impregnation under support. So basically, the solution has been impregnated on silica or alumina. You thermally treat it, so you remove the ligands, and you are left with a very small, highly dispersed metal particle that mimics the composition of the molecular precursor. And that was the hope we had. That was verified by X-ray analysis. So you do not have, under this condition, phase segregation. You retain an intimate interaction between the metal centers. And I think that's often what is needed in heterogeneous catalysis. If you want to combine activity and selectivity, the bimetallic effects only apply if the two metals can see each other, can feel each other strongly. If they're far apart, no way. Then you would have a consecutive transformation. Oh yeah, yes, you're right. I mean, if you just decompose the molecular species with no support, you end up with a dark residue, which if you do that under inert atmosphere, which just be the metals. But these metals could still be interesting to study for other applications. For catalysis, it wouldn't be very helpful, because in catalysis, you want to reach high dispersion. You want to have maximum active surface. So small particles. You don't want to have a chunk of metal. In your car, you don't want to have a chunk of platinum or iridium for the car exhaust. You want to have highly dispersed particles with less content and mostly active surface around. That's the challenge here. Well, as I said, you mean the cubane subunits? Yeah, the cubane subunits, as you say, the molten cofactors, there was still the debate, what is at the center? People thought it was nitrogen, now the latest used as carbon, which still is not fully explained. But anyway, these cubane motifs are also in nitrogenase, the iron 4 cofactor. All this system seems to be recurrent, probably because they are amenable to multi-redox changes without fragmentation. These cubanes can breathe. You add, you pump electron, you give electron, the cubane structure retains. It will expand or shrink, but it will not decompose. Yeah. That's probably why they were selected.
Okay, so it's mostly pure like a reductive condensation of the two different.
If you wish, although the detailed growth mechanism is not known. It's impossible to know exactly what are the various steps leading to the final structure. But in retrospect, you can view these as built from such subunits, which are complete or incomplete cubanes. And of course, the nature of the ligands will be important because they have to bridge. So they have to have the capacity to doubly bridge, triply bridge, or even more. But you're absolutely right. These motifs are interesting in their own right because they are recurrent throughout many areas of chemistry. Yeah, in these cases we can. Nickel remains always nickel 2, and we know sodium 1. So in these cases we have no ambiguity. If you started doing redox chemistry and add, for example, 1 electron at a time to get a mixed valence species, then the game would be more complicated. Like in the iron 4, it's formalism. Globally you have added 1 electron, but you cannot tell to which of the 4 irons because they were symmetry equivalent. True, you're absolutely right. That was the idea, to make the system more soluble, and we did, and we found the system more active. But in order to prepare that mixed sodium-nickel cluster in high yields selectively, turned out to be rather complicated. This is why it took so long to grow single crystals of that compound, because we don't really know, but we had enough to do catalysis, and indeed the catalysis turned out to be higher in terms of activity, because this compound is more soluble.
Well, was it because of the solubility or the change in the electronic structure?
Well, when you vary 2 factors at the same time, it's always difficult to answer. My gut feeling, it's nothing more than that, it's solubility. Because we saw that in the precursor case, without the sodium system, there's the nickel one. We could not dissolve all the pre-catalysts in the reactor. So probably during catalysis, it was being dissolved because the temperature increases because of the co-catalyst. But you're absolutely right. We cannot rule out an electronic effect of the sodium directly or indirectly affecting the ligands and therefore affecting the nickel center. But the first reaction I would have is to say, well, it did affect the solubility clearly. It may not be the only factor, but certainly is a key factor. But the surprise was the presence of the sodium, because if you take another base instead of sodium hydride, another one you can think of, then you may have a different aggregate. That's right. So we tried many, but I can only talk about those which crystallized.
Yeah, just another very key question. You commented on some interesting magnetic properties. In some of those, I think the simplest one was
the cubane nickel 4. Yeah, correct.
Right, nickels in the molecule. What was the say at least hysteresis or the super paramagnetic to ferromagnetic phase transition temperature at which you could
yeah, these were low temperature, very low temperature properties, very low temperature. So we had Vansdorfer in Grenoble to look at that. He has his own squid, which goes to 200ths of a degree. It's absolutely crazy. So they're not going to be the SMMs of tomorrow.
Correct.
In terms of properties, because it's too low. It's too low.
Right, that's not what I was thinking of.
No, but just for, no, it was very low.
Right. A lot of these 16 wheels.
Exactly.
Larger,
exactly.
So this is around 2 Kelvin or larger?
Right, exactly, around 2 kelvins.
Okay, so it's really very, very low, right?
Yeah.
Which I guess one would assume based
Yeah,
on the number of
exactly.
Okay, I think now that it's almost 4:30, we better stop here.
Again, apologize for being too long. And
Ask you to join me in thanking Pierre Braunstein for running.
thank you.